April 15th, 1945. Elbe River, Germany. The telegram that arrived at 3rd Army headquarters carried 3 words that made every tank commander's blood run cold. All bridges destroyed. For 72 hours, Patton's armored divisions had been racing toward Berlin, covering ground faster than any army in military history. Then the Elbe River appeared. 200 feet of rushing water and German demolitions that had dropped every span into the current. The mathematics were brutal. Build a bridge, lose 3 days. 3 days meant the Soviets would reach Berlin first. Lieutenant Colonel Wesley Yale stood on the western bank, watching German artillery ranging the obvious crossing points. Every engineer in 3rd Army knew the solution. Bailey bridges could span the Elbe in 48 hours, but 48 hours of construction under direct fire would cost hundreds of casualties. The Germans had learned to target bridge-building operations with devastating effectiveness. Then Yale remembered something he'd seen 6 months earlier at a training demonstration in England. A civilian engineer named Donald Roebling had shown them a vehicle so strange that most officers dismissed it immediately. An armored box that could swim like a boat and crawl like a tank. The military brass had laughed at it. Roebling's prototype sat abandoned in a supply depot 200 miles behind the front lines. Nobody wanted swimming tanks, when the real problem was building bridges fast enough to keep pace with armor. But Yale understood something his superiors had missed. What if you didn't need bridges at all?
October 7th, 1935. Clearwater, Florida. Donald Roebling sat in his workshop, staring at a photograph that haunted him. Hurricane victims clinging to rooftops in the Everglades, surrounded by water too shallow for boats, too deep for vehicles. Rescue workers had watched helplessly as people died just yards away, separated by an impassable swamp that defeated every conventional vehicle. The newspaper headline burned into his memory: 17 dead in Everglades rescue failure. Roebling came from a family of engineers. His grandfather had designed the Brooklyn Bridge. His father had pioneered wire rope manufacturing. Engineering excellence was the family business. But Donald had chosen a different path, inventing solutions for problems others considered unsolvable. The Everglades rescue disaster revealed a fundamental gap in human capability. No vehicle existed that could operate in both water and on land. Boats couldn't cross shallow marshes. Trucks couldn't float. Amphibious operations required specialized equipment, trained crews, and conditions that never matched actual emergencies. Roebling's solutions seemed absurd at first glance. Build a vehicle shaped like a boat, but powered like a tank. Give it tracks that could propel it through water while providing traction on land. Create a hull that could survive waves while carrying meaningful cargo. Every engineer he consulted explained why it couldn't work. Too heavy to float, too light to provide meaningful carrying capacity. The tracks would act as anchors in water. The hull shape would make it unstable on land. But Roebling remembered something his grandfather had taught him. Complex problems often require simple solutions that look impossible until someone builds them.
March 12, 1937. Roebling's Clearwater Workshop. The first prototype sat in 12 feet of water, slowly sinking. Roebling watched $15,000 of his personal fortune disappear beneath the surface, along with 18 months of work. The mathematics had seemed perfect on paper. The hull displacement should have supported 3 tons of vehicle weight plus cargo. Instead, water poured through track openings faster than bilge pumps could remove it. His chief mechanic, James Harrison, a former Navy machinist, pulled the prototype back to shore using block and tackle. "Mr. Roebling, sir, I've worked on every type of floating equipment the Navy operates. This concept violates fundamental principles of marine design. Tracks create massive water resistance. The hull shape is too boxy for efficient displacement. We're fighting physics itself." Harrison's skepticism reflected broader engineering consensus. Marine architects insisted that efficient water vehicles required streamlined hulls and propeller propulsion. Tank designers argued that effective tracked vehicles needed rigid chassis and heavy armor. Combining both requirements seemed to violate the laws of physics. But Roebling studied the failure with an inventor's eye for unexpected insights. The prototype hadn't capsized. It had maintained stability even while sinking. The tracks had actually provided directional control in water, something propeller-driven boats struggled to achieve in swamp conditions. The problems were solvable through incremental improvements rather than fundamental redesign. The second prototype incorporated larger flotation chambers sealed independently to prevent progressive flooding. Revised track designs featured hollow metal plates that provided propulsion in water while maintaining traction on land. The hull received reinforced seams at stress points where water pressure had forced leaks. Testing resumed on May 3, 1937. The revised prototype entered the water with Roebling at the controls, accompanied by Harrison and two local reporters who'd been covering his attempts with increasing skepticism. The vehicle floated. Not elegantly, not gracefully, but it stayed on the surface with 6 inches of freeboard. Roebling engaged the tracks. The vehicle moved forward through the water at 3 miles per hour, slower than swimming speed, but moving nonetheless. The real test came when Roebling drove toward the shoreline. Conventional boats required careful beaching procedures to prevent hull damage. The amphibian simply drove out of the water and up the sandy bank without hesitation. The transition from water to land took 7 seconds. One reporter later wrote, "I watched a vehicle that is simultaneously the worst boat and worst truck I've ever seen, yet somehow accomplishes what neither boats nor trucks can do alone."
November 20th, 1940. United States Marine Corps Headquarters, Washington, D.C. Major General Thomas Holcomb read the field intelligence report from Tarawa with growing alarm. Marine Corps planners had wargamed Pacific Island assaults using conventional landing craft. The scenarios assumed boats could reach beaches where troops would disembark under cover of naval gunfire. But Tarawa's coral reefs extended 800 yards from shore, too shallow for conventional landing craft, too deep for waiting infantry. Japanese defenders would have 800 yards of unobstructed killing zone where Marines would be completely exposed. The casualty projections were catastrophic. Estimated losses, 40 to 60% of the first wave. Acceptable losses? None. The Marine Corps needed a solution that didn't exist. Lieutenant Colonel Krulak had attended Roebling's demonstration in Florida 6 months earlier. His report sat buried in Marine Corps archives, dismissed as interesting but irrelevant. Krulak had written, "Civilian inventor has created swamp rescue vehicle with potential military applications. Recommend further evaluation." Holcomb retrieved Krulak's report and read it carefully. The vehicle could operate in shallow water where landing craft grounded. It could drive onto beaches without requiring ramps or piers. The armored hull could protect troops during the approach. On December 3, 1940, Holcomb sent a telegram to Clearwater, Florida. "Mr. Roebling, Marine Corps requires demonstration of amphibious vehicle capabilities. Military specifications attached. Can you deliver?" Roebling's response arrived 3 days later. "I build rescue vehicles, not weapons of war." The Marine Corps tried again, this time with a different approach. "Mr. Roebling, Marines will conduct rescue operations on Pacific Islands where casualties will number in thousands without proper equipment. Your vehicle could save American lives." This message hit its target. Roebling replied by telegram, "Send specifications. We'll begin work immediately." June 15, 1941. Dunedin, Florida test site. Roebling's military prototype weighed 9 tons, carried 24 fully equipped Marines, and featured armor plating thick enough to stop rifle fire. The transformation from swamp rescue vehicle to military assault craft had required complete redesign of every major system. Major Victor Krulak watched the demonstration with a mix of hope and doubt. The Marine Corps had committed $30,000 to this project, substantial funding in 1941 dollars. If the vehicle failed, Krulak's reputation would sink with it. The test course simulated Pacific assault conditions. 400 yards of open water, shallow coral reef section, sandy beach, and 15-degree inland slope. Conventional landing craft couldn't complete this course. Infantry couldn't survive crossing it under fire. Roebling started the engine, a Hispano-Suiza aircraft power plant modified for marine use. The vehicle entered the water with surprising grace for a 9-ton armored box. The tracks engaged, driving it forward through the waves at 6 miles per hour. Krulak timed the water crossing, 4 minutes 20 seconds. The vehicle reached the coral reef section where conventional boats would ground. Instead of stopping, the amphibians simply drove across the reef, tracks finding purchase on the coral while maintaining forward momentum. Transition to beach occurred smoothly. The vehicle drove out of the water and up the sand slope without hesitation. Total time from water entry to inland position, 7 minutes 15 seconds. Krulak calculated the tactical implications. A conventional assault required landing craft to approach the beach, lower ramps, disembark troops, and withdraw. Minimum time under fire, 12 to 15 minutes. Roebling's vehicle could deliver troops from ship to inland positions in under 8 minutes, while providing armored protection throughout the approach. The mathematics were revolutionary. Assault casualties could drop by 70% if troops never exposed themselves during beach landings. General Holcomb's assessment was immediate and decisive. Roebling, the Marine Corps requires 200 of these vehicles. When can production begin? Roebling's answer shocked everyone present. Never. I'm an inventor, not a manufacturer. I don't have production facilities for military equipment.
September 8, 1941. Food Machinery Corporation, Lakeland, Florida. The meeting between Donald Roebling and FMC executives represented an unlikely partnership. FMC manufactured agricultural equipment, tractors, harvesters, industrial machinery. Military vehicles were outside their expertise. But FMC's president, John Bean, understood industrial capacity. His factories could produce heavy machinery using mass production techniques. If Roebling's design could be simplified for manufacturing, FMC could deliver vehicles faster and cheaper than specialized military contractors. The challenge was staggering. Roebling's prototype was essentially hand-built, custom components assembled through trial and error. Military production required standardized parts, manufactured by the thousands. FMC's chief engineer, Robert Ingersoll, spent 3 weeks analyzing Roebling's design. His report highlighted the fundamental problem. This vehicle incorporates 347 custom components that would require specialized tooling. Production timeline, 18 months minimum before first delivery. 18 months was unacceptable. The Marine Corps needed vehicles immediately for training and deployment to the Pacific Theater. Roebling made a decision that would prove crucial to Allied victory. He released all patent rights to the military for $1, eliminating the legal obstacles that typically delayed government procurement. Then he worked with FMC engineers to redesign every component for mass production. The revised design incorporated off-the-shelf parts wherever possible. The Hispano-Suiza aircraft engine was replaced with a Cadillac V8, readily available and easy to maintain. Custom armor plates became standardized sheets cut from stock steel. Specialized tracks were redesigned using conventional tank track components modified for water propulsion. By November 1941, FMC had transformed Roebling's hand-built prototype into the Landing Vehicle Tract, LVT, a production model that could be manufactured at scale. The first production order, 200 vehicles designated LVT-1. Delivery schedule, June 1942. Cost per unit,
$12,000. Then, December 7th happened.
December 8th, 1941. Emergency War Production Board meeting, Washington, D.C. Pearl Harbor had changed everything. The Pacific War that military planners expected in 1943 had arrived 2 years early. Marine Corps amphibious assault plans that assumed gradual equipment procurement now required immediate implementation. The original order for 200 LVTs became obsolete within 24 hours. The Marine Corps revised requirements, 1,000 vehicles minimum, delivered within 6 months. FMC's production capacity was already at maximum, serving agricultural equipment contracts. Meeting military demands required complete factory conversion, a process that typically took 18 months. Instead, FMC accomplished the transformation in 60 days. Agricultural machinery production lines were shut down, retooled, and restarted building amphibious vehicles. Tractor manufacturing equipment was modified to produce LVT components. Combine harvester assembly lines began fabricating armored hulls. By March 1942, FMC was producing 30 LVTs monthly. By June, production reached 50 per month. By September, 75 monthly. The impossible manufacturing timeline became reality through industrial improvisation that mirrored Roebling's engineering creativity.
August 7th, 1942. Guadalcanal, Solomon Islands, 0641 hours. The first combat test of Roebling's design began at dawn. 53 LVTs carrying Marines of the 1st Division drove toward Guadalcanal's beaches through light surf and scattered Japanese rifle fire. Lieutenant Michael Moreno commanded the lead vehicle. His training had been minimal, 3 weeks of vehicle familiarization in New Zealand. Nobody knew how LVTs would perform under combat conditions. The Marine Corps was essentially conducting a live experiment with men's lives at stake. Moreno's LVT entered the surf zone at 6 miles per hour. Japanese defenders on the beach opened fire immediately. Rifle bullets sparked off the armored hull, but none penetrated. The vehicle approached a coral reef section that would have stopped conventional landing craft dead. Instead, the tracks found purchase on the coral, driving the LVT across the reef and through shallow water beyond. The vehicle reached the beach and drove directly inland, depositing Marines 50 yards from the water's edge in covered positions. Total time from ship to inland deployment, 6 minutes 40 seconds. Marine casualties during landing, 0 from Moreno's vehicle. By 0830 hours, all 53 LVTs had completed their beach runs. Total landing casualties, 14 wounded, none killed during the approach. For comparison, conventional landings at similar defended beaches typically produced 30 to 40% casualties during the approach phase. Moreno's after-action report was blunt. The LVT saved my life and the lives of every Marine in my vehicle. Without it, we would have been slaughtered crossing that reef.
November 20th, 1943. Tarawa Atoll, Gilbert Islands. The operation that had terrified Marine planners was finally happening. Tarawa's coral reefs extended 800 yards from shore, an impossible killing zone for conventional assault methods. Major General Julian Smith committed 125 LVTs to the first wave, carrying 3,000 Marines toward the most heavily defended beach in the Pacific. Japanese defenders had fortified Tarawa with bunkers, machine gun positions, and artillery pre-registered on every approach route. The landing craft carrying follow-up waves grounded on the coral reef exactly as predicted. Marines attempting to wade 800 yards under fire suffered catastrophic casualties. Within the first hour, 400 men were killed or wounded crossing the reef. But the LVTs drove across the coral reef without stopping.
The vehicles delivered Marines directly onto the beach and 30 yards inland before disembarking troops behind armored protection. Corporal John Spaulding later wrote, "I watched men in landing craft dying in the water 600 yards from shore. I watched my LVT drive right past them and put us on the beach alive. The difference between dying and surviving was Roebling's vehicle." By the end of the first day, casualty statistics told the story. Marines delivered by LVT suffered 12% casualties during the approach. Marines forced to wade from grounded landing craft suffered 54% casualties. The impossible vehicle that military brass had dismissed now carried an undeniable record. It saved lives in precisely the conditions where conventional equipment failed catastrophically.
March 10, 1944. Bougainville, Solomon Islands. The tactical applications expanded as commanders discovered capabilities Roebling himself hadn't anticipated. Colonel William Barba faced a problem common throughout the Pacific: swampy terrain that stopped conventional vehicles completely. Japanese defenders had retreated into interior swamps, assuming they were safe from American armor. Tanks couldn't cross the marshland. Trucks sank in mud. Artillery couldn't be positioned to support infantry advances. Barba requisitioned 20 LVTs and used them as armored personnel carriers in swamp terrain. The vehicles that were designed to cross 400 yards of ocean could also navigate through mangrove swamps that defeated every other vehicle type. Japanese defenders never anticipated armored vehicles emerging from swamps they considered impassable. The tactical surprise enabled American forces to flank positions that would have required frontal assaults with massive casualties. The versatility that emerged from Roebling's simple concept, a vehicle that operates in water and on land, created tactical options that reshaped Pacific campaign strategies.
June 6, 1944. Normandy, France. 0630 hours. The European application of Roebling's design demonstrated engineering flexibility that surprised even the inventor. The LVT-4, modified specifically for European conditions, featured a rear ramp that enabled rapid troop deployment and cargo loading. The 4th Infantry Division used 36 LVTs to assault Utah Beach. The vehicles drove through the surf, across mine-cleared sections, and inland to positions where conventional vehicles would have been stopped by beach obstacles. General Theodore Roosevelt Jr. crossed Utah Beach in an LVT, becoming the only general officer in the first assault wave. His presence demonstrated command confidence in Roebling's design that would have been unthinkable with conventional landing craft. British forces at Sword Beach adopted LVTs for specialized roles, carrying engineers and demolition equipment through surf zones, delivering command elements directly to forward positions, evacuating wounded from beaches under fire. The versatility proved that Roebling's original insight, solving the Everglades rescue problem, had created a vehicle applicable to entirely different challenges across multiple theaters.
April 15, 1945. Elbe River, Germany. Lieutenant Colonel Wesley Yale's gamble was about to pay off, or cost him his career. He'd requisitioned every LVT from supply depots across Third Army's rear areas, 62 vehicles that were supposed to be in training or maintenance. General Patton had given him 24 hours to span the Elbe River. Building Bailey bridges would take 3 days minimum. Yale proposed something unprecedented: use LVTs as floating bridge components. The concept seemed insane. LVTs were personnel carriers, not bridge sections. But Yale had calculated the possibilities. Each LVT could support 10 tons of weight while floating. If vehicles were positioned side by side across the river and anchored, they could create a floating bridge strong enough for tank traffic.
At 1430 hours, the first tank approached Yale's improvised bridge. 62 LVTs anchored in place, spanning 200 feet of the Elbe. The tank weighed 35 tons. The LVT bridge was entirely theoretical. The tank drove onto the first LVT. The vehicle settled in the water but maintained position. The tank continued across, moving from one LVT to the next. Total crossing time? 3 minutes, 20 seconds. By 1700 hours, an entire armored division had crossed the Elbe on Yale's LVT bridge. Patton's advance continued without the 3-day delay that building conventional bridges would have required. Yale's innovation proved that Roebling's vehicle was more versatile than anyone, including Roebling himself, had imagined.
August 15th, 1945. VJ Day. Roebling's Clearwater Workshop. Donald Roebling read the production statistics with quiet amazement. 18,620 LVTs manufactured during the war, deployed across every theater, from North Africa to Okinawa. Marine casualties reduced by estimated 8,000 lives compared to conventional assault methods. General Holland Smith's official assessment arrived by courier. The LVT was the single most important piece of equipment in the Pacific War. Without it, island assault operations would have been prohibitively costly, perhaps impossible. Roebling had never sought military applications. His original goal remained simple: save lives during rescue operations. The war had transformed his invention into a tool of battle, but the fundamental purpose remained unchanged: getting people safely across impossible barriers. The civilian inventor who had built a rescue vehicle for Everglades victims had inadvertently created the technology that enabled Allied victory in 2 oceans.
The LVT's influence extended far beyond World War II. Modern amphibious assault vehicles still use Roebling's basic concept: tracked vehicles that can operate in water and on land. The U.S. Marine Corps AAV-7, in service from 1972 to 2020, was a direct descendant of Roebling's original design. Civilian applications emerged in disaster relief. Organizations discovered that amphibious tracked vehicles could reach flood victims in precisely the conditions that had inspired Roebling's original invention. Hurricane rescue operations in Louisiana, Texas, and Florida employed vehicles descended from his Everglades rescue design. Donald Roebling died in 1959, having transformed from civilian inventor to inadvertent military innovator. His greatest achievement wasn't the vehicle itself, it was proving that solutions to impossible problems often come from unexpected sources. The military establishment dismissed his design initially because it looked ridiculous: a box on tracks that couldn't swim properly and couldn't drive efficiently. But Roebling understood something professional engineers had missed. Sometimes adequate performance in 2 environments beats optimal performance in 1. U.S. tanks crossed rivers without bridges because a civilian inventor had solved a completely different problem: rescuing people from Everglades swamps. His solution just happened to work equally well carrying Marines across coral reefs, soldiers across Normandy beaches, and entire armored divisions across German rivers. The impossible idea succeeded because Roebling never accepted that complex problems required complex solutions. Sometimes the answer was simple: build a vehicle that swims and drives, even if engineers insist it can't do either properly. In the end, Roebling's greatest innovation wasn't engineering, it was perspective. He looked at an impassable barrier and asked the question nobody else considered: what if we don't need bridges at all?